Morning, Syed.
Good morning. How are you?
Doing? Not too bad. Let's see here. Okay. Morning, Syed.
Good morning.
Okay. Okay, let's let everyone through. Morning, everyone.
Good morning, Professor.
How are you doing?
Hi, I'm good.
Good.
I want to ask, did you, by any chance, log on Piazza and maybe see a very recent post about our discussion on Tuesday's lecture from last week?
No, let me check.
Okay, it's quite, yeah. It's about some extra resources for the homework. Yeah, I stated some points that I didn't really get through last time, and yeah, if you have time, then if you go through it, it will be really much of a help.
Yeah, I mean I'm almost. So the TAs, each of them was producing a sketch of a result. I mean, of a assignment answer.
Yeah.
And so we're going to distribute those soon. I'm just waiting for one last one.
Okay, that's great. Thank you for all this.
It should be coming
Appreciate
down the pipe. Okay, let me just get this sharing thing working. Okay, so we've been talking about linear operators, and we're about to so we're about to get to some interesting results. Okay, let's see. So what our goal? Our goal from now until so for this week, what I want to do is give a complete classification of linear operators on finite dimensional vector space. So the goal is to present a complete classification of linear operators on finite dimensional vector spaces. Okay, but in order to do this complete classification, we're going to use spectral theory. So we're going to use the theory of eigenvalues and eigenvectors, which you just did an assignment on. And the problem, well, the nature of that theory is that in order to know that there is an eigenvalue, in order to be guaranteed at least one eigenvalue, we need to be working over C in general. So we're going to be doing this classification over the complex numbers. It doesn't mean that over other fields you cannot have eigenvalues. Of course, over any field you can have plenty of diagonal matrices. And you can take those matrices and you can change basis so that they don't look diagonal anymore. So there's plenty of diagonal matrices over any field. But in order to be guaranteed that you have some eigenvalues, you need to be working over C. Okay. And the type of classification that we're going to do has a name. It's called the Jordan canonical form. And this is the analog of the cycle notation that we studied for bijections of finite sets. The cycle notation for permutations of a set of n elements. Okay, so in other words, so let me put it in a different way. So more precisely or explicitly, we want to show that every operator, remember that an operator is just a linear map from the vector space to itself. Every operator A from V to V, where V is finite dimensional over C, is conjugate, sometimes called similar, to one in Jordan form, i.e. we can choose a basis beta for V, such that the matrix of A in this basis has a very special form, okay, which is called the Jordan form. Okay, now, okay, so let me. I find that when you're learning the Jordan canonical form, it's one of those rare cases where it's useful to know what the answer is before you learn the theory, because really, in order to discover this classification, what you would have to do is you'd have to study a whole bunch of examples first to get a feel for what kind of linear operators there are out there. And well, we don't have that kind of time to do that kind of experimentation in class. But I should at least show you what the Jordan form is so that you know what the goal is. Okay, so let me just let me just introduce the Jordan form, the way that they release software. So I'm going to first release absolute junk, meaning that it's not the Jordan form, and then I'm going to improve it so that it's just slightly less terrible each step, until finally, after many years, you finally get something that's usable. So, for example, ideally, we would want this type of answer, which is that the matrix is diagonalizable. Okay, this is a Jordan form, but the problem is that, that's not how life is. Life is not simple like this. You cannot expect that every operator is diagonalizable. You cannot expect to find a basis which consists essentially of fixed points, in the sense that the linear operator just takes each basis vector to itself multiplied by a scalar. Okay, so this is too simple. This is okay, but too simple. And here, what I really mean here is, I really mean the simplest possible situation where lambda I is not equal to lambda j. So that's like a particularly like naive, simple idea that maybe there are n completely different eigenvalues, and each one of them has an eigenvector, and that's the way that the matrix diagonalizes. Okay, so this is not quite right. So let me go to the version 2. So in version 2, we allow the possibility of repeated eigenvalues. So we have, let's say, lambda 1, lambda I1, lambda I1, a certain number of times. Let's say you have like K1 times the same eigenvalue. And then you have another eigenvalue, lambda I2. Well, actually, let me just call this lambda 1. Lambda 1, lambda 1. Then lambda 2 comes, and we have a certain number of lambda 2s, K2, and so on. And there are K eigenvalues, or maybe P eigenvalues. And there's Kp of these. And the sum K1 plus K2 plus Kp is equal to n. Okay, this is called a, I can rewrite this in the following way. So I can think of these as blocks. Like this. Where each block is lambda times the identity matrix, which is a K1 by K1 identity matrix. That's what you get in the first block. The second block has lambda 2 times the K2 by K2 identity matrix, and so on. So this is the same as that. I'm just rewriting it as lambda 1 times an identity. Then the next block is lambda 2 times the identity. Okay. So this is just repeated eigenvalues. Okay, so this is, well, okay, this is not really an improvement of the software. This is just adding features which are useless because this is a special case in a way of the format of the first one. It's just that we're allowing equal eigenvalues. So this is okay. This is in Jordan form, but too simple. Okay, so let's, okay, so now what we want is, so this is the first time that you really get something that's closer to the right answer, which is that you should be allowing what's called a Jordan block. So here's your eigenvalue. That's repeated a certain number of times. But instead of having zeros, we have a 1 on the first diagonal, and then we have zeros elsewhere. And this forms a block, which is called a Jordan block. With eigenvalue lambda. So this is like J lambda 4. It's a 4x4 Jordan block with eigenvalue lambda. And you could imagine having blocks of these types. Let's say this was lambda 1. Okay, and let's say that there were n of these, so I'll call it jk1 of lambda 1. And suppose that there were several of these. Okay, and so it's a K1 by K1 Jordan block. So the key point about this is that the way that it acts is in more of a cyclic pattern, so that when you apply the operator to the first basis element, it is an eigenvector. So it's just multiplied by itself. but then the next one is almost an eigenvector. You get the second basis element is multiplied by lambda 1, but you get a remainder and you get a multiple 1 of the previous basis element. So every time that you apply the operator to a basis element, you get this kind of scaling behavior plus the previous basis element is always tagging along, right? And so you get this kind of cyclic type behavior, which we're going to study today. Okay, but the point is that this Jordan block can be accompanied by other Jordan blocks, lambda 2. This would be j k2 of lambda 2, and so on. Okay, and the special case is that if it's a 1-by-1 Jordan block, then you end up with something that looks like this. You could think of these as little 1-by-1 Jordan blocks. So this is the first kind of good version of the software. You call it version 1.0. Okay, it's okay, but still too simple. Okay, and then the final one, so the Jordan form, looks like this. So what we're gonna do is first look at lambda 1. So lambda 1 can occur in a block, a Jordan block like this. But then it can occur again in another Jordan block of a maybe different size. So there's several of these Jordan blocks with the same eigenvalue. I'll just put the dots here. Okay, so we have a kind of big block, okay, which has in it j k1 lambda 1 j, I don't want to have too many indices, but let's see. So let's say I'll call it jl1 lambda 1, jl2 lambda 1, all the way to jl j lambda 1. So there are j Jordan blocks with the same eigenvalue, such that L1 plus plus Lj is equal to, let's say, K1. That's the total size that is devoted to the eigenvalue lambda 1. Okay, and then you have this entire thing repeated for the next eigenvalue. So every eigenvalue is treated the same. Oh, except, of course, this should be lambda 2. And we get our we start to get our blocks. And the whole thing looks like that. So if you stare at this thing, what you would see in the matrix is that you'd have a single eigenvalue all the way down here, And then just above that diagonal, you would have a sequence of ones and then a zero, a sequence of ones and then a zero, a sequence of ones and a zero. Okay. And so this pattern, like in order to know the matrix, so this means that the Jordan form is determined by a sequence L1, L2, J1. Let me call this J1. Let me call this is K2, and this is J2. So we have lambda 1 has this sequence of Jordan blocks associated to it. And then lambda 2 has a sequence L, let's see. Sorry for this. The notation is not important. I just wanted to be clear. Lambda 2 has its own sequence. Which may be of a different length, and so on. You need to know what the eigenvalues are, and you need to know what the sizes of the blocks, the Jordan blocks for that eigenvalue are. If you know that information, then you know the Jordan form. So that means that every operator, we should be able to assign this data. We should be able to assign a bunch of eigenvalues, and for each eigenvalue, a sequence of numbers. These numbers tell you the sizes of the Jordan blocks for that eigenvalue. Okay. Any questions about this? So at this point, we have no idea why this is this is the case, but I just want to make sure that what I'm saying here is correct. This is the final version. This is correct.
So Charlie has a question.
Yeah, go ahead.
Yeah, just to confirm, in the final version, to the right of all of the lambdas in the Jordan block, they have a 1, right? Except for the very last one that has a 0 next to it, right? Or nothing next to it if it's at the very end of the matrix.
Yeah, all of the entries on the, what you do is you just draw a square, you put lambda down the middle, and on the diagonal immediately above it, you put ones.
Yeah, and then in the sort of places between the corners, or where the blocks kind of touch, there's a 0 in between those two, right?
You mean here?
Yeah.
Yeah, there's everything here is 0. Yeah.
Okay.
Everything that is not written is a 0.
All right, cool. Thank you.
So Long Tai has a question.
So the last version will fit every operators.
Correct. Every operator, as long as you are in a complex vector space.
Yeah.
As long as you're dealing with the complex numbers, every operator will look like this. Over the real numbers, it is not true that they will not look like that. It turns out that in the real case, each of these 1 by 1 pieces, each of the numbers that I've drawn here becomes a 2 by 2 matrix. This becomes a 2 by 2 matrix. This becomes a 2 by 2 identity matrix. This is a 2 by 2 matrix, which is the same as that one, and so on. And this is because over the real numbers, we are not able to diagonalize a rotation. So what will happen here is instead of lambda 1, you're going to have a rotation by a certain angle and a multiplication by a certain scale. So there will be some, all of these little things will be 2 by 2, but it will look roughly the same. But anyway, that's not important. The important thing is to understand the complex one.
Okay, and we'll go through more details about this, like why this.
Yeah. I mean, I have to understand why in the world is this true? Yeah.
Yeah. Okay. Thank you.
Anything else about this?
Yeah, so Sung has a question.
Yeah, so I didn't really get the reasoning behind why there would be elements of 1 above each diagonal elements.
Right. So I'm not explaining that yet, but I will. Yeah, I will.
Okay.
It's not It's not obvious. Okay. But I just what's important right now is not to understand why, but it's to understand the behavior that it does. So, for example, if you stare at this thing, what it means is that the first basis element is an eigenvector. You see that?
Yes.
Yeah. And the second element is not an eigenvector, but it's almost. So if I apply the operator, you do get lambda 1 times the second basis element. But then there's this error term, which is the previous basis element. Right? So it's it's like you have a leader in the group of kids, and then you ask this guy a question, and he always just kind of refers to his friend, the leader. And then this one always refers to the previous friend. So this is the leader, and these are all the followers, right? So this is like this block, this Jordan block is kind of like a trend, So these are the followers of the trend, but the leader is the eigenvector. But the interesting thing is that for this block, we have several leaders. We have one leader here, E1, and then at some point you're going to find another basis vector, which is another eigenvector. So I'm just going to highlight that here. So this, and this, and however many else you have, these represent eigenvectors. Okay. So what I really mean, let me be more precise, just so that there's no confusion. Okay. Remember that up here we have the basis, right? E1 is sent to this column. E2 is sent to this column. Okay, this is going to be now L1 plus 1 is going to be sent to this column, and at some point you're going to get a whole bunch of basis vectors here. And the point is that this one, and so on, these ones are the eigenvectors. Okay, and these ones here are generalized eigenvectors. So the generalized eigenvectors are the followers. So we have the leaders are the eigenvectors, and then the others are the generalized eigenvectors. Actually, the generalized eigenvectors include the eigenvectors, but I'm just saying that the others are not eigenvectors, but they are still generalized eigenvectors. Okay, any other questions?
Yeah, so Elliot has a question.
At the beginning, we wrote like Jordan canonical, and now we have Jordan here. So is that the same thing? Or?
Yes, same thing. Yeah.
And is there like the word canonical? I think I've heard you say like the word canonical basis.
Canonical just means natural. Canonical just means natural. Like it used to be that everyone who was well educated would have to learn Latin and Greek and all of the so-called great books, which were written throughout the Renaissance and so on, and that's the canon, the literary canon. And so
I see.
This is the Jordan canonical form. It's the it's the one true religion. That kind of thing.
Thank you.
You're welcome. Okay, so let's start in our analysis here to see how we get to this thing. Okay, so Right. Okay, so let me just collect my notes here. Okay, so the main result that we need to use is it's a very fundamental thing about a linear operator. So so the first thing I need to use is that there exists a polynomial P of Z, complex coefficients. Okay, wait, so let me start again. So let V be our finite dimensional vector space over C, and let T be a linear operator. So it's a map from V to itself. Okay. Number one is the fact that there is a polynomial P of Z. You know, it's something like sum of AI Z to the I. Such that this polynomial, if I apply it to T, we get 0. And this would not be a very interesting statement unless I said that the polynomial was non-zero. Okay. Now, let me just correct this. The way that I phrase this makes it seem as if there's that there's only one. But of course, if I have a polynomial expression in T, which vanishes, then I can multiply that by any other polynomial in T, and the product will also vanish. So that means that there's tons and tons of polynomials with this property. So let me change it to there are non-zero polynomials such that P of T is equal to 0. Okay, so so sometimes that's obvious. So for example, if T was lambda times the identity, then we would know that T minus lambda would be 0. And so therefore I can take the polynomial to be Z minus lambda. Or any multiple thereof. Okay, and if I plug in T into Z, and I understand that lambda is, whenever you see a constant, it's intended to mean that it's a constant times the identity, right? Then you see that the polynomial, the matrix or the operator actually satisfies this polynomial. It's a root of this polynomial. Is there any questions about what I've just said? This really simple example. It's like the most obvious example. Any questions about that? Is there anything confusing about it? Let me do the next example. Let's suppose that T was lambda 1 lambda 2, lambda n, diagonalizable, diagonal, right? Then my polynomial I could take to be like this, t minus lambda 1, sorry, z minus lambda 1, multiplied by z minus lambda 2, multiplied by z minus lambda n. Okay, why does that work? Well, let me explain. So let me do a simple case. Suppose that t was lambda 1, lambda 2. Right, then t minus lambda 1 times t minus lambda 2 would be like this. I would have a 0 here, and I would have lambda 2 minus lambda 1. So that's the first term. And then the next factor is lambda 1 minus lambda 2, 0, 0, 0. Okay, so by removing lambda 1, I kill the first entry on the diagonal. By removing lambda 2, I kill the second entry on the diagonal. Now, these individually are not 0, as you can see, because the eigenvalues might be distinct. However, when I multiply these two things together, I'm just going to multiply this with this and this with this. So I'm going to get 0. Okay, so if you have n eigenvalues to kill, right? If there's n eigenvalues, you just have to remove one, multiply it by the next, by the next, by the next, and then you're sure that this big polynomial will kill the operator. The other thing to notice is that so there might be someone who starts to freak out, because they would notice the following fact, that as we all know, polynomials are commutative, right? So if I have a polynomial in X and I factorize it in one order, and if I reverse the order, that's going to be the same polynomial, because the polynomials form a commutative ring, a commutative algebra, commutative multiplication, AB, P1, P2 equals P2, P1. Okay, but then you might freak out because this is an operator, and we know that operators do not commute necessarily. S times T is not the same as T times S. So what's going on here? Well, the important thing is that I'm only using one operator, T. T always commutes with T. T always commutes with T times T, right? So as long as you're only interested in one operator, your one true love, the one operator, that operator will always commute with itself. It will always commute with its powers. And so it behaves like Z, the way that the variable Z behaves. Okay, anyway, that's the next one. Okay, now, what about if I had something like this? Okay, well, if you took Z minus lambda, then you would get T minus lambda times the identity. That would be 0, 1, 0, 0. Okay, so this is not a polynomial that kills this operator. So how do we get one? Well, notice that if we took this and squared it, right, then we would get 0, 1, 0, 0 times 0, 1, 0, 0. And this only sees this, and we have zeros. So this is 0. So whenever you see a matrix like this is just an aside. Okay, if you see a matrix like this, right, then what happens when you square it? Well, if you take this row and multiply through, you're going to hit something at the end. So you're going to get 0, 0, 1. So the square of this is not 0, but if I take another power, I'm going to be multiplying this matrix by this, and you can see that you don't get anything. You just get zeros. So in other words, okay, and if I keep going with this type of example, 0, 1, 0, 1, 0, 1, 0. Okay, if I square this, if this, I'll call this n. This n squared would be, zeros down the diagonal, zeros above, and then ones, 1, 1, 0. And then n cubed would be 1. And finally, n to the 4 would be 0. So you see how this works. It's like, the soldiers, they march. You have the soldiers here. You square the matrix. They go up in one diagonal, and then they go to the next diagonal. But eventually there's the cliff, and they all fall over the cliff. These types of matrices, these are called, this type of matrix, this type of operator, n, with the property n to the k is equal to 0 for some k, is called nilpotent. Okay, and these are a very important class of operators. They're nilpotent because they have the potential to be 0 if they just try hard enough. Okay, so I just wanted to give you an aside on this nilpotent idea because that's exactly what we have. T minus lambda is now in the formation of the soldiers in their starting position. And if we square it, we get 0. So that means that the polynomial is z minus lambda squared. Okay, and just to give you one last example, okay, if we had two Jordan blocks, let's say lambda, 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 1, 1, mu, mu, 1, can you give me an example of a polynomial which would kill this matrix? Anyone?
Diba?
Would it just be each of the factors to kill the individual nilpotent matrices?
Just tell me the answer.
Oh, z minus lambda squared times z minus mu.
So is z minus mu going to kill that little piece there?
Squared
That
again.
2 by 2 piece? If you take z minus mu, is that going to be 0?
No.
It's going to be in the starting position of the soldiers, 0, 1, 0, 0.
So square it again as well.
Yeah, so this should be squared, and what should be the power here?
Cubed?
Yeah.
Okay, I see. Off by 1 error.
Yeah. Okay, is that starting to get a bit clearer about the polynomials that kill an operator? Any questions about these? So how do we know that there exists such a polynomial? Okay, so let's prove it. So the proof, there's many ways to prove this. Let me just give you a really simple way to prove it. Just start taking all the powers and just list them all. Just process of boredom. You start with 1. You start with t. You start with t and then t squared, t cubed. Okay, so I'm just getting more and more of these linear operators. What is a polynomial? A polynomial is a linear combination of these. That's what a polynomial is. So how do I know that there will be a linear combination of these things which equals 0? Well, these are all vectors. In the vector space of linear operators. We can add linear operators, we can multiply by scale. We already saw this, that the vector space of linear operators, LVV, is finite dimensional. It has dimension n squared, where n is the dimension of V. So that means that it's limited. It's very limited. It's a finite space, right? The space of these operators. And I just have this list, which is getting longer and longer. Well, at some point, I can stop, because once I get to n squared, then the length of my list, this may be familiar to you, the length of the list is longer than the dimension of the space. And the list has length n squared plus 1, which is greater than the dimension of the linear operators. Therefore, there must be a linear dependence. Done. There is a polynomial that kills t. So there is a polynomial of degree less than or equal to n squared that kills t. Any questions about this?
Isaac, you have a question?
Yeah. Can you just like you said, in dimension L is like n squared, but why there's like n equal to dimension V? Is that like just a mistake, or did I miss something?
If you have a vector space V,
Oh, yeah, I get it
to
now.
the n, then the linear operators from V to V, those are like n by n matrices. And so they have dimension n squared.
Thanks.
You're welcome.
Okay, so Neil has a question.
So it looks like this, at least all the examples so far, right? The polynomial has only been no more than degree n. So is there a way to turn this down? It's n squared bound.
Yes, definitely. So in fact, there exists a polynomial of degree less than or equal to n, which kills. And often it's less than n, but we're going to get to that in a moment.
All right, so Daniel has a question.
Hi, Professor.
Hi.
I just have a question. I don't understand the conclusion. Why is it that this polynomial exists if this list is linearly dependent?
The reason is that a polynomial is a linear combination of these powers. That's what a polynomial is. It's a sum of coefficients, ai, multiplied by t to the I.
Are we taking this list as a basis for the dimension of operators? I mean, for the space of operators?
Yes, we want to, but we don't know. I mean, t could be 0, for example. We don't know if it's a basis, but we know that if you write n squared plus 1 of them, then it's already bigger than the dimension of the operators. So there must be a dependence between them.
I see. That makes a little bit more sense. Thank you.
So for example, if you were doing 2 by 2 matrices, that would be of dimension 4. So we would just take the identity, we take the matrix squared, the matrix cubed, and the matrix to the 4th power, that would be 5 matrices in a 4-dimensional space. So they must be linearly dependent.
Thank you.
You're welcome. Okay, so the resulting polynomial may not be minimal. Okay, so there's a nice theorem or proposition that there exists a unique minimal monic polynomial for each operator. Monic just means that the leading coefficient is 1. The highest coefficient of the highest power is equal to 1. Okay, and the way that you prove this is just by what's called the Euclidean algorithm, or in other words, the division of polynomials. So you prove this by using the Euclidean algorithm, which is otherwise known as long division of polynomials. Okay, so in other words, you can say that yeah, that you could say, like, consider all the possible polynomials that kill the operator, and take one of them that has the least degree. You start by choosing a polynomial of least degree such that P of t is equal to 0, right? And then what you show is that if you try to divide, if you have any other polynomial, that any other such polynomial, Q, must be divisible by P. Why? The reason is because if you divide P into this bigger polynomial, you're going to get it's going to divide a certain amount, and then there's going to be a remainder. Okay, but that remainder has to be of degree less than the thing you're trying to divide by. Okay, and that remainder would kill T. So so that means that the remainder must be 0. It must be right. So I don't want to make, it's in the book, you can look at it. I don't want to, what I'm saying is that it's completely obvious, right? What you do is you say, suppose that you have a whole bunch of polynomials that kill T. Some of them will have a minimum degree. You don't know how many, but there will be some with minimum degree. And you choose one. And if you take any other polynomial that kills T, that minimum degree one must divide it evenly. So that means that every other polynomial that kills T must be a multiple of one basic polynomial of minimum degree. And that is called the minimal polynomial. The reason why it works is because if you take one of the smallest degree polynomials and you try to do long division, you will get a remainder of even smaller degree. And that remainder will have to kill T, because the thing that I'm dividing already kills T. Right? I'm taking something that kills T, I'm dividing it by something else that kills T. So that means that the remainder must also kill T. And that would be a contradiction, right? Because we're assumed that the thing we chose to divide by is of minimal degree. let me maybe just write a little bit, since the remainder, any remainder must be 0, since it has degree less than p. Yeah. Okay, I didn't realize that I went a little bit over. We have a test at 12:10, so in 6 minutes. So let me stop here, and sorry about the shortened break. You have 6 minutes break, and it's a Quercus test. Quercus test. Okay, we'll be back at 12:16.
Professor, I don't see a test.
Don't worry, it should be coming up. I set a timer, so it'll show up at a certain time. Okay, let's. Hopefully that was not too difficult. Question?
So Daniel
Yeah.
has a question.
Yeah, Professor.
Yeah.
In question 1, I noticed you never stated that U was finite dimensional. So
Right.
how can we apply rank nullity theorem to this and conclude that U must have dimension 6?
Well, that's a good question. So we have a linear map from U to V, and we know that the null space is finite dimensional, and we know that the range is finite dimensional. So that's more than what you know in the rank nullity theorem, right? So I'm presenting you information in a slightly different situation. I'm not telling you in advance that the dimension of U is finite. I'm just telling you that the null space of T and the range of T are finite. So you should be able to conclude from that U is finite. But you're correct that you should use the rank nullity theorem in this question.
So
there's a lot of questions, but I'm not sure if they're about the quiz or about the class. Let's take one more question.
All right, so Andy has a question.
Andy?
All right, if Andy's not there, Omar has a question.
Yeah, the question 2, it stated that for T is a linear operator on finite dimensional vector space V.
Yeah.
And we're supposed to select the true statements.
Yeah.
It said if null space of T is 0, it consists of 0 vector only, then T must be an isomorphism.
Yeah.
So that's true. And another, the last 2 are true, but it just says the correct answer is the first one.
Oh, really?
We don't get points. Yeah, we don't get points for the last 2. I'm not sure if the first. I think the first one is correct as well, but we don't get any points for the last 2. So we just get points for 1.
I'll check that. Yeah, I can fix that if it's the case. Question 2, you're saying, right?
Yeah.
Sorry, my internet died.
Okay, I'll fix that later. Don't worry about it.
All right then. Thank you.
Is there anything urgent, or can I continue?
Yeah. Sorry, did I cut somebody off?
Go ahead.
Yeah, I was just going to say for question 1, it says that. So one of the options is there is no constraint on the dimension of V, and apparently that is a correct answer, but there is a constraint on the dimension of V, which it has to be greater than or equal to 4 because the range of T has dimension 4. So I was confused by that, why it's being marked as wrong. Yes.
Yeah, you're right about that.
Okay, great.
Yeah, I'll fix that.
Thank you.
Anything else?
All right, so Elliot, you have a question?
Go ahead.
Sorry, that was for the quiz. It was answered already.
Okay, Jack.
Sorry, that was my hand up from before. Sorry.
Okay. All right. Let's. Oh, what happened? It's not sharing anymore. Okay, 1 second. Okay, so we need a small lemma in order to get the main result of classification of linear maps, and it's a innocent-looking lemma, and it goes like this. Suppose that you have vector spaces U, V, and W, and suppose you have maps T and S. And we're going to assume that null space of T and null space of S are finite dimensional. So what I mean by this is that let us have vector spaces U, V, W and maps T and S with the null space of T and the null space of S finite dimensional. Okay, so let me draw a picture of the null space of S. So we have 0 in W, and there will be a subspace of V which will be sent by S to 0. So this here, this is the null space of S. And inside there, we have 0. Okay, and this is the null space of T. So it's the set of vectors. I'm drawing like a Venn type diagram, okay? It's not supposed to be accurate in terms of the way it looks, but at least it's accurate from the point of view of sets. So we have a bunch of vectors in V, a subspace of V, which is the null space of S. And yeah, and we have a similar space, null T, inside of U, which is the null space of T. Okay, and the statement of the statement of this lemma is about the dimension of the null space of the composition. So the dimension of the composition, which is ST, the null space of ST. Okay, so what is this dimension? So I'm going to tell you the statement of the theorem in a second, but what is this dimension? So what is killed by the composition? One thing is for sure, that anything in the null space of T is definitely going to be sent to 0 because it's already sent to 0 on the first step. So this will be at least the dimension of the null space of T. But it will have, it may have more because because, you know, the stuff that is killed by the composition is not just the stuff that is getting killed at the first step. Okay, it is the stuff that is sent in the first step to things which are killed by the second step. So what we need to do is we need to go and look at all the stuff in U which is sent to the null space of S. Okay, this stuff is the null space of ST. Okay, so I just want to make it clear that the null space of ST is potentially larger than the null space of T. Okay, and what is that extra correction? Well, so there's another space here which is maybe important, and that's the range of T. So I didn't draw the range of T. So the range of T is going to be where this map T sends all of you that one is more difficult to draw because it may not contain the null space of S completely. Okay, so what the statement here is that, the extra stuff is going to be the dimension of the null space. Let me just move this over. Okay, so this formula is basically telling us what we need to know about the nullity of a composition. The stuff that is killed in the two steps has two parts. The first part is the stuff that's already killed in the first step. The second part is the elements of the range of T which lie inside the null space of the second step. Okay, and let me just prove this. Not difficult to prove. What's difficult is to figure out the statement, not the proof. The proof is easy once you have the statement. So first of all, note that the null space of T is obviously contained inside the null space of ST. That's obvious. Anything killed by T is going to be killed by ST. And so the second thing to note is that if we have a point which is in the null space of ST, then what that means is that T of U is in the null space of S. And of course, T of U is also in the image of T, just because it's T of something. So this means that T of U is inside the intersection of the null space of S and the image of T. Sorry, image is the same as range. I don't know, I prefer image, but I'll use the textbook's notation. Okay, so these two comments are just getting us ready. It's basically saying that something that's killed by T is definitely in the null space of ST. And if something is in the null space of ST, then when I apply T to it, after the first step, it must be killed in the second step. And so it must be in this intersection. Okay, so now to prove this, if I look at the formula, it looks a lot like the rank nullity theorem. It's the sum of dimensions on the right-hand side and the dimension on the left-hand side. But in order to apply the rank nullity theorem, the big one, the one that's the sum of the two things, this has to be the vector space, which is the domain of the map, right? If I have a linear map from V to W, then the dimension of V is the one that's the sum of the null space and the image. So I want to, so the strategy is to use the rank nullity theorem for the vector space null space of ST. So how do we do that? Well, so let's let T0 be the restriction of T to the subspace the null space of ST. Okay, that's what I'm going to do. I'm going to restrict my attention to this operator, but instead of viewing it as a map from U to V, I'm going to restrict it only to this orange region, which is the null space of ST. And then I'm going to apply the rank nullity theorem to that operator, to that map, the map from the orange to V. That map will have a null space, and it will have a range, and so we can apply the rank nullity theorem. So apply the rank nullity theorem to T0. Okay, so how do we do that? So what is the null space of T0? The null space of T0 is well, what is killed? So if I restrict this to null of ST, then we know that the null space of T is already in there, right? So that means that what is T going to kill if I restrict T to this space? Well, the only thing it can possibly kill is something in the null space, but the entire null space of T is contained in here. So that means that the null space is not going to change. The null space is still going to be the null space of T by comment 1. That's good because now I have the dimension of my space, which is here, and I have the null space of T, which is here. All I need is this. Okay, so the null space, that's 1. And the range, what is the range? Well, the range of T0, right? If you look at this, if you apply T to something in the null space, that will be in the null space of S and in the range of T, so it will be in this intersection. So we get the second part like this. So therefore, the dimension of the null space of ST is equal to the dimension of the null space of T plus the dimension of the null S intersect range T. So it's you could say that this is a corollary of the rank nullity theorem. It's basically telling you when you compose two maps, how do we figure out the null space or the nullity of the composition? It's it requires you to know the null space of the last map and the range of the null space and range of the last map and the null space of the second, the first map to compute this. Okay. So now let's use this. Let's kind of let's prove a theorem which is called the decomposition theorem. Okay. So let T be a linear operator on V. V finite dimensional over C. And let P of Z be a polynomial such that P of T is equal to 0, which we just proved before that exists. A non-zero polynomial, and I'm going to factor the polynomial. So the polynomial will be like this: Z minus A1 to the N1 product Z minus A K to the NK. Okay. So then we get a decomposition. V decomposes as a direct sum V is, let's say V1 direct sum of subspaces, V1 plus V2 plus up to Vk, where each of these VIs is the null space of T minus AI to the Ni. Okay, so the idea is, if we go back to the Jordan form, okay, you see here that the operator has these blocks, these big blocks, and each of the blocks is associated to an eigenvalue, lambda 1, lambda 2, and so on. Actually, let me just call these numbers, let me call these numbers lambda I, because that's what they are. Okay, so the point is that this, when we put the matrix into this Jordan type, we get these blocks, right? These blocks correspond to basis, a certain set of the basis elements. The first K basis elements are participating in one Jordan block. And then the next basis elements are in the next block, and so on. Okay, and so we can split the basis into these pieces where the operator acts as a single Jordan block. That's what these VIs are. So the first few basis elements which participate in the first Jordan block, they will be spanning V1. And the next group is V2. Okay, so okay, and so the decomposition theorem is getting us ready to split the vector space into pieces, and each one of these pieces is only going to experience one eigenvalue. Okay, so we're getting a separation of the vector space into distinct parts, a direct sum according to the roots of the polynomial that kills t. Any questions about the statement of the theorem? This is a first step. We need to separate the vector space into these pieces. The next step, which I'm going to do on Thursday, is that I need to choose the basis for each one of these VIs so that the matrix will be in Jordan form. But first I need to do this splitting so that I get the big blocks. Then I can worry about the form of each block, the way it looks. So any questions about this statement? So far, the claim is that you figure out the polynomial that kills t, you factor it, you take each factor with a single root, right? You produce this operator, so you produce a bunch of operators, right? You take t minus lambda I to the ni. There's going to be k of these operators, which are made from t. And then we're going to look at the null space of these, and we're going to get k subspaces. And the cool thing is that they give a direct sum. This is very much analogous to the theorem that we proved before, that if you have two eigenvectors with distinct eigenvalues, then they are linearly independent. So this is a particular case of that. Or, sorry, that is a particular case of this theorem. Sorry, go ahead, Omar.
Oh, not just a simple, like, just to make sure. This whole Jordan canonical form and this theorem only works for when the number of eigenvalues is the same as the dimension, right?
No.
Like we have as many.
No. Well, I'm not sure what you mean, because if you look at the Jordan form, okay, all of this block only has one eigenvalue. So you could have a Jordan matrix, which is just this block, in which case there would only be one eigenvalue, and the dimension would be whatever, 100.
But there would be 100 eigenvectors in that case, or?
No. See, look, the important thing about the Jordan block is that the first basis element is an eigenvector, because when I apply E1, when I apply t to E1, I get lambda 1 times E1. When I apply t to E2, I get lambda 1 times E2 plus E1 because of this 1 here. Remember that the way you read a matrix is that the rows are labeled E1, E2, E3, right? The columns E1, E2, E3. And this matrix tells you where E1 is sent, where E2 is sent, where E3 is sent. So E1 is sent to a multiple of itself, but E2 is not. E2 is sent to a multiple plus the previous guy, E1. So this is an eigenvector, but these are not. All of these represent non-eigenvectors. This one is another eigenvector. These are not. So in this picture, if you just consider these three blocks, right, we could have a 100-dimensional space, but with only 3 eigenvectors, all of which have eigenvalue lambda. And then the rest of the space, there's other vectors which are not eigenvectors. Okay, you're still at version 1. Version before the release, right? It's not necessarily true that you can find these vectors, these eigenvectors. They won't exist. there will be some eigenvectors, but not necessarily n of them. Okay, next question.
Thank you.
You're welcome.
So Long Tai has a question.
Yeah, I'm a bit confused. Like, shouldn't there be a coefficient like in front of the factorization of the polynomial?
The minimal polynomial, you could, whatever, let's say you find a minimal polynomial that kills the matrix, right? There will be a leading term, the biggest coefficient, the biggest power of z will have a coefficient. You can just get rid of that. Just divide by that, because it'll still kill the matrix. So, your polynomial, if the definition of the minimal polynomial is that it has the smallest degree, which kills, so it has to kill t, it has to have the smallest degree, and it has to be monic, which means that the coefficient of the top degree part has to be 1. So there's a coefficient 1 of z to the nk. If I multiplied this all out, this would be like z to the n1 plus n2 plus nk plus more coefficients. But the leading coefficient would be 1.
Oh, that's the definition of the monic.
Sorry?
That's the definition of the monic.
Monic means that the top power has a 1 coefficient.
Oh, okay. Okay, that is okay. Thank you.
Yeah.
All right. So Isaac has a question.
Yeah, go ahead.
Yeah, Professor, I just want to ask, like, if you single out one Jordan block and come to a 1 by n n by 1 matrix, that would look like binomial, right?
Sorry, if you take a single Jordan block and then you do what?
Like n by 1 matrix, like x1, x2, something like that, and you will get some sort of binomial, right?
You could do it yourself here. I'm not sure, but what you get is lambda x plus y. You get lambda y plus z, and you get lambda z.
So not necessarily. Okay.
It's not really binomial. It's more like a cyclic thing that you get it's something that looks like eigenvalues, but it's always adding the previous guy. So you always get this additional term.
Okay. And also for the last one, the last theorem, it's just the number of v is just number of eigenvalues, right? Distinct eigenvalues.
Say it again.
The number of v's in the direct sum is just the number of distinct eigenvalues, right?
Yeah, it's the number of these terms. It's this same as k. Yeah, lambda 1 up to lambda k. This is the same k.
Yeah, thanks. Just want to clarify. Yeah, thank you.
Okay, so let's prove this. This is a really important result. It's basically giving us the fundamental way of thinking, of analyzing a linear operator, because it allows us to break up our space into pieces, which are more simple, and then we're going to analyze on Thursday the simple pieces. Okay, so first, what we're going to prove is that so let W be the sum, and we're going to prove that it's direct. Okay, so that just means that, so i.e., we need to prove that if we have V1, if we have VI inside VI, and if there's a linear relation, V1 plus V2 plus up to VK, if we have a bunch of vectors, one in each of the factors, and if the sum is equal to 0, then we want to show that VI is equal to 0 for all I. So in other words, we want to show that the different VI subspaces, that these are linearly independent. Okay, so that the vector space is a direct sum of these subspaces. So we just want to show that the subspaces are linearly independent in this sense. Okay, so all right, so okay, so we're supposed, so this is very similar to the proof which is in your reading and which I spoke about at the office hour, about the fact that eigenvectors with distinct eigenvalues, so this is similar to the statement that eigenvectors with distinct eigenvalues are linearly independent. This is the favorite statement of physicists. They always use this in quantum mechanics, that if you have two vectors, two states of with different quantum numbers or eigenvalues, then the states are linearly independent. Okay, so it's similar with this. So, but I'm going to prove it in a nice way. So what we'll do is we need to show Vi is equal to 0 for all I. So let's do that. So the way that we'll do that is we'll define an operator Si, and I'm going to let this operator be the product of, I'm going to do like all of these factors except for the one that is used, except for the one that corresponds to Vi. So I'll take t minus lambda 1 to the n1, t minus lambda 2 to the n2, and so on. But the t minus lambda I to the ni, I don't put it. I remove that factor. So in other words, I want it to be the product of all j not equal to I of t minus lambda j to the nj. So we now have a, we get new operators S1 up to Sk operators. Okay. Okay, and okay, and then I'm just going to apply this operator Si to both sides of the equation. Say, so I'll get Si of V1 plus Vk equals Si of 0 is equal to 0. Okay, and then what you see is that each of these VIs, each of these VJs is in the null space of t minus lambda j to the nj. So if there is a t minus lambda j to the nj, if that is present, it will kill the corresponding VJ. So, because t minus lambda 1 to the n1 is in Si, because this factor is allowed here, this will kill V1 by definition of V1. And this one here will kill V2. Okay, everything will be killed except for the one that corresponds to Vi. And I will get this is equal to Si of Vi only. So we know that Si of Vi is equal to 0 because Si kills all the others. Okay, so we need to conclude we want to conclude that vi is equal to 0. For this, we need to know that Si is invertible on the null space of T minus lambda I to the Ni. So what we're going to do is show that Si is invertible on the space in which Vi is. Then I can apply the inverse, and I'll just get Vi is equal to 0. To this, and get Vi is equal to 0. So actually, the time is running out. So what I'll do is I'll complete this on Thursday. On Thursday, what we'll do is complete the proof of this. And once we have that, we should be able to quickly obtain the Jordan canonical form. And that'll give me some, that'll give us some time to do some other topics. I'm hoping to do to spend some time in the last couple of weeks on determinants and and tensors. I think that you should learn a little bit about tensors and a little bit about determinants. And then if you finish this class with a knowledge of the Jordan form, determinants, and tensors, I think you'll be in good shape. Okay. I'll take a couple questions, but see you on Thursday.
Okay, so Isaac has a question.
Yeah, hi, Professor.
Hi.
I just want to know, you have post the lecture notes before, but it seems stopped for last 2 weeks. So I want to ask if you can.
No, they're up on the web page.
Yeah, I checked for a few days ago. They're not there.
They are
for
there.
The reason was okay.
They're
Okay,
there.
yeah. And also, you mentioned that this is in the textbot, right? Is that in chapter 8? So if we want to revisit this
Yeah,
kind
I
of
think that's
knowledge-
right. Yeah, that's right. Let me just check. Yes. Chapter 8 is let me just check which part. That's correct. This is the material in chapter 8, which I'm going to cover it in a little bit maybe a little bit faster and more efficient way, but you should read chapter 8. Chapter 8 is the last thing that you would read, but you don't have to read the entire thing. 8D is what the Jordan form is about. The thing is that the nice thing about chapter 8 is that it does not depend in any way on 7 or 6. That's for 247. But the Jordan form doesn't use inner products, which is why I think it should be included in MAT240. Whereas in 247, you really have this new object to study, which is the inner product. Yeah, chapter 8.
Yes, thank you.
Okay, so Deba has a question.
Yes, I just wanted to go back right at the start when you went through all the different versions building up to the Jordan form.
Yeah.
And my question is kind of for the linear operators that are diagonalizable, do we still have an incentive to put them into the Jordan form if we can just take the diagonalized matrix instead?
The diagonal matrix is in Jordan form.
But it doesn't.
This is a 1-by-1 Jordan block.
Oh,
Jordan
so you
block
don't
always-
need the little ones.
Well, if it's 1-by-1, then there's no room for them.
Yeah. Okay.
Yeah.
Okay, I understand. Thank you.
You're welcome. Okay, everyone. See you on Thursday. Bye.
Thank you, Professor.
Thanks a lot, Syed.
Thank you.
Thank you.
You're welcome.